to study the structure. Now the question is why we study the structure of the crystalline solid. Why it is important to study the structure, right? So here is some examples. The main thing why we study the structure is we discussed in the first week also that the properties of materials are directly related to their crystal structure. So I showed you even the example in the coming slides I will show, but materials having different crystal structures, even if they have the same composition, so the properties are changed, right? They have different properties. So for that reason, the structure of the materials we have to study, of the solid material we will study, and that's why it is important. Like for example, if we have a magnesium and beryllium, they have these two materials have one crystal structure and are much more brittle, right? These materials. While on the other side, if we have gold and silver, these two materials have different crystal structure and they are not that much brittle as of the magnesium and beryllium. So the gold and silver are ductile, right? While magnesium and beryllium are brittle material and they have different crystal structures, right? So significant property differences exist between the crystalline and non-crystalline material, even if they have the same composition, right? So like for example, the non-crystalline ceramics and polymers, normally they are optically transparent. And in the same material, in crystalline or semi-crystalline form, they tends to be opaque or translucent, right? I showed you an example in the first week. We have here the aluminum oxide, right? This is the same material, aluminum oxide, this one, and this one. So here we have single crystal, here we have the polycrystalline material, and here also the polycrystalline material with some porosity. Now here, if you look into the material, the same aluminum oxide is completely transparent. Here it is not completely transparent, but still it is like translucent. And if you see here, this material is completely opaque. Although this material has the same aluminum oxide, the same composition, but because of the crystal structure, they have different optical properties. So same way, the properties can be different, not even optical, even the mechanical, the electrical, all the properties. Right? And the processing structure and the properties and performance scheme that we discussed in the first week, if you have a crystal structure of iron and if you heat treated it, right? If you heat it to improve their mechanical properties, so the structure will be changed. So the structure of the material has a relation with the properties, right? And as I told you, the properties, of course, decide for which application we will be using the material. So in today's class, we will be studying the crystalline solid and their structure, the crystal structure of the solid material, right? So what is the crystalline material? So we will start from here. Now, solid material, they may be classified according to the regularity with which the atoms ions are arranged. We know that all the materials are made of atoms and ions, right? So how the atoms and ions are arranged, on the basis of that, we decide whether it is crystalline or non-crystalline. If the atoms and ions are arranged in a repeating periodic configuration, if we have a material, let's say, and we have the 4 atoms here, and these 4 atoms are arranged, repeating again and again in the whole structure, right? In the same way, it means it is crystalline material because this unit is repeating again and again, right? So whenever there is a repeating order of the atoms and ion within a material, we call that material a crystalline material. If this order of atoms is random, like it is somewhere here, we don't see any specific order, then we can say it is non-crystalline. So that is long-range order exists such that upon solidification, the atoms will position themselves in a repetitive 3-dimensional pattern. Now, every material we are studying, we don't study in 2-dimensional, right? We study in 3-dimensional. So it should be in 3-dimensional. The arrangement should be in 3 dimensions. It should repeat itself in 3 dimensions, right? So in which each atom is bonded to the nearest neighbor atom. Now in this, if you look into this box, so in this box, if you fill it with the atoms, right? So each atom, of course, it is connected to some neighbor atom. And these neighbor atom must be the same, right? Like every atom connected to 4 other member atoms. So it will be same. Even here, this atom will be connected to 4 other. This atom will also be connected to 4 other. And this atom will also be connected to 4 others. This thing will repeat in the whole structure. And we call it coordination number. We will discuss it today. but this should be there, and that material we call it crystalline material. All metals, many ceramics material, and certain polymers form crystalline structure under normal solidification condition. So different material like metals, ceramic material, some polymers also, they have the crystalline structure. We will discuss in today's class the different crystalline structure, and I will give you the example which material has which structure. And those materials which are non-crystalline, this long-range atomic order is not exist in the material, right? Like the order, it is the same like this one, not like this one. So those material are non-crystalline, or sometimes we call it amorphous material. And we will discuss the amorphous or non-crystalline in next class, right? So this class we will only discuss the crystalline material, right? Now look here, we have the crystal structure, or sometimes it is known as lattice. So what we have here, the crystal structure, how it looks like and how it will be. So here something we have made just to make the things clear, right? In reality, it is not like this. This is just an imagination. Here, look, this is that 3D object. If we have the material and all the atoms, you see these balls, the spheres, these are the atoms. So they are arranged in a proper order, right? And what we study, whenever we are studying the crystalline structure, we don't need to study the whole thing, right? We take some portion of it. And what portion we take? We take a portion which is repeating again and again in the whole structure. And that is known as a unit cell. And we take that unit cell, and then we study that unit cell. Now from here we have taken this thing, and we can represent it in this form, or we can represent this in this form. This one is known as the hard sphere unit cell. And this one is known as the reduced sphere unit cell. Now look into the reduced sphere unit cell. These balls are one atom, right? So each ball represents one atom. But keep it in mind, in reality, this is not the case. Like we have one atom, then we have this line, and then here we have another atom. This is not the case. This is just for the representation, right? It doesn't mean the material will have this small atom and the whole space will be empty. No, there is empty spaces. We will discuss it today. But the reduced space, the unit cell sphere is just the representation of a unit cell, right? In reality, it is not the case. In reality, the atoms are arranged in this way, right? So we have the atom, they are closely packed. Now look here, if this is one portion of the atom, this is another. So this atom and this atom, they are very close to each other. So when you look here, they seems to be very far, but that one is just the representation, right? So here, keep it in mind that the atoms arrange themselves in 3D, and we don't need to study the whole structure. We will take a small part of it and we will study that one, right? And that small part is known as what? Is known as unit cell, right? So the unit cell, it is actually the building blocks of the crystal structure. So you know, you might have studied in your schools in biology. They are saying the cell is the building block of the human body, of all living organism, right? Similarly here, the unit cell is the building block of the crystal structure, or you can say the brick, or the what you call the taboo. This is the building block of the wall or the construction, right? So here, this is the unit cell is the building block. Now the atomic order in the crystalline solid indicates that small groups of atom form a repetitive pattern. And that small groups of atom is known as the unit cell. Now unit cell is not a single atom, right? It is a group of atoms. That group is repeating within the whole crystal structure. Thus, in describing a crystal structure, it is often convenient to subdivide the structure into small repeated entities called unit cell. And different structures have different types of unit cell. Now here you see we have a simple cubic unit cell. This is known as simple cubic unit cell. And we have other also, we will discuss it. Now here, look, this is the structure in 3D. You see, this is the structure of the material. In this whole structure, what is happening? There is a structure, small group of atoms that is repeating again and again. And look here, this one, in 3D, look into this one. This is one cube. And if you look here, this is, again, this is the cube, right? The same cube. Here also, the same cube, right? and so on. So what does it mean? It means that this small groups of atom is repeating again and again. And that is known as a unit cell. This is the important thing of this slide. The unit cell is the basic structure unit or building blocks of the crystal structure and define the crystal structure by virtue of its geometry and the atom position within. So this geometry, if we have a unit cell like this one, the simple cubic unit cell, we will study in the coming classes the geometry, like the x direction, what is happening to y, the z direction, the angle between x and y, the angle between y and z, and all these. So this geometry we will also study. Now, we will study only the metallic crystal structure, right? So in the metallic crystal structure, the material have different types of unit cell. That different unit cell is repeating again and again. So for metal, using the hard sphere model for the crystal structure, each sphere represent an iron core. Now, three famous are the most important three famous structures are there, right? Which are present in almost all the metals. But only one metal, there is only one element, right? Which exhibit the simple cubic structure. This one, the simple cubic structure, this occurs only in one element, which is polonium. While the remaining all the atoms, they have these three types of structure, which is the face center cube, the body center cube, and hexagonal closed packed structure. Look here into the image. We have the body center cube. Now, before this, you saw the simple cubic, right? Simple cubic structure was having what? That one was having only atoms at the corner of the cube, right? Like these are the atoms. Here we have at the corner, but one atom we have in the center of the cube. Here look, we have this atom in the center of the cube, and we call it body center cube. And different materials have this structure. We will study the body center cube in detail. We have the face center cube. In the face center cube, what happens? The cube is, if you look into the cube, it looks like your dice, right? The Ludo dice. Now on each face, there is one atom. And on each corner, there is an atom attached. Now we will study whether this is a complete atom or a part of the atom, right? But it is there. So look here, we have on each, this is in the top face, bottom face, left, right, and back and front. So these 6 atoms are on the faces of the cube. And of course, there are on the corner as well. So this is known as face center cube or FCC, right? We call this FCC in short. And this one we call BCC. And this one we call HCP. So the HCP, hexagonal closed packed structure, what is there? We have a hexagonal structure. Now here it is not a simple cube, right? This is a hexagonal structure. So here at the bottom we have a hexagonal structure, right? And it has 6 atoms at each corner and 1 atom in the center of the hexagonal structure. Now this hexagonal is connected to another hexagonal layer like this. Here you see at the top, this is another hexagonal structure and 1 atom is at the center. Between these two hexagonal plane, we have another plane which has only 3 atoms, right? It is between the two. And this type of structure is known as hexagonal closed packed structure. Now, from here, we will start to study each one of them. And we will study how many atoms are there, what is the coordination number of the unit cell, right? And how the atoms are closely packed in the different types of unit cell. So this we will study in detail today. Clear? Any confusion? Wherever there is a confusion, ask me, right? Today you have to be mentally present. This is a very important class and there is some imagination, right? The things you have to imagine in 3D. Otherwise, then it will be difficult for you. But you have to be present mentally, right? Now here, the number of atoms in a unit cell of the simple cubic, right? So we have a simple cube. This is the simple cubic you see here, which is the building blocks of the polonium atom, right? Now we have to find how many atoms are there in the unit cell of the simple cubic structure. So as I told you, we have different atoms like this in 3D. They are arranged, right? So look and imagine this in 3D, right? Now here something is repeating, right? And we have to take a part of that is repeating in the whole structure, and that is known as the unit cell. So for representation, what we have taken, we have cut this part like this, you see, from here to here to here and here, and we have taken it here. This is the unit cell, or you can say the simple cubic unit cell. Now we have to think how many complete atoms are there. Now keep it in mind, this one ball is, this sphere is a single atom, right? This one sphere ball is what? A single atom. Now in the unit cell, the simple cubic unit cell, how many complete atoms are there? If you look into this, the hard sphere, the simple cubic, on the corner, one atom is attached, but that is not a complete atom. So this is 1/8 of the atom, right? And again, this is again 1/8 of the atom. Here 1/8 of the atom, because there are 8 corners. You see 1, 2, 3, 4, 5, 6, 7, and 1 at the back is 8. Now, if there are 8 parts of the atom and each part is 1/8, so how much it will be? 8 multiplied by 1/8, we will get 1 atom. So what does it mean? It means in the unit cell of simple cubic structure, we have 1 complete atom. If you combine all these, you bring this here, this one here, this one here, so it will make a single sphere. And the number of atoms in a simple cubic structure, a unit cell of simple cubic, is 1. Is it clear to you? Okay, good. This is the reduced sphere. We discussed it already. This is just the representation. Now the coordination number. As I told you, in the whole crystal structure, each atom is attached to its neighbor atom, right? And though the whole thing is repeating. Now we have to find out, in the simple cubic structure, a single atom is attached to how many other atoms? How many neighbors that atom has, right? So look here, we have the 3D structure. And if we take example of this atom, you see here, so it is connected to 6 other atoms, right? Look here, 1, 2, 3, you can see this is connected to 6 atoms. This is just imagine it in 3D, right? Now here, what will happen? This atom, this will be connected to 6 other atoms. How? Look here, this is connected to this atom, connected to this atom, and it is connected to this atom, right? Only 3 here. But the remaining 3 will be on the here. And if you imagine it in 3D, so the 3 will be on the other side. So total 6 number of atoms are the neighbors of this atom, right? Or you can say the nearest neighbors, which are in contact, right? For the coordination number, it is important that the atom is in contact with how many other atoms. By neighbor doesn't mean like this is the neighbor of this one, right? No. These two do not have direct contact. So we will not count this in the coordination number. All those atoms which are connected to the atom, right? This is known as the coordination number. And in the simple cubic structure, the single atom is connected to 6 other atoms. That's why the coordination number of the simple cubic unit cell is 6. Right? The coordination number, you understand? What is the coordination number? Guys, are you sleeping or with me? Okay. We have the next thing, which is the atomic packing factor. Now, the atomic packing factor, I told you we will discuss how the atoms are packed in a unit cell, right? So that is known as the atomic packing factor. Now, if we have the unit cell here, let's say this is the unit cell. Now, in this unit cell, we have the atom, or you can say here, look, this is the unit cell. So now the atoms are packed in this way, right? They are connected to each other. But if you see, we have the free space here. Too much free space is there, right? So to know how the atoms are closely packed in that unit cell is known as atomic packing factor. So in some structure, it will be the free space will be too much. In some, it will be less, right? And in other, it might be very less, right? So this is we have to understand. If the atoms are closely packed, it means in a small space there are too much atom. So it might be the material might be dense, right? And if we have like the atom too much free space, then it will be light. So this is known as the atomic packing factor. Now for the atomic packing factor, we use the formula, the volume of atoms in a unit cell. Now in the unit cell of simple cubic structure, how many atoms are there? Only one atom, right? So the volume of this one atom divided by the total unit cell volume. The total unit cell volume is what is the total unit cell volume? If this is a unit cell and this side, let's say this is A, so this will also be A, and this side is also A. So the total unit cell volume will be how much? AQ, right? And the volume of the atom within the unit cell. So in the unit cell, volume of the atom will be how much? Volume of this part plus this part plus this part plus this part plus this part, this part and this part. We are not counting in this one the volume of the atom, the free space is not coming. But in the total unit cell volume, the free space volume is coming. So for that, it is important so that we know that how many atoms are there. If there is one atom, so we take the volume of only one atom, right? So this is known as the atomic packing factor. Now we will find the atomic packing factor in the simple cubic structure. Look here, here we have the simple cubic structure, and this side is, let's say this is equal to A, right? This side is equal to A. Now, what is the formula? The formula is the volume of the atoms in a unit cell divided by total volume of the unit cell. Now here, if you look into all the sphere, better look here. You look into the sphere. From here to here, this line represents what? In geometry, what is this? 0.5A, okay, yes. This is 0.5A because this total is A. So this is 0.5A. But in other words, we can say that this is the radius of the sphere. This is the radius of the sphere. So a sphere is what? Sphere is a complete atom. So this is the radius of the atom. So means we can also say that 2R is equal to A, right? We can also say in this way. So now coming here to find the volume of the atoms in the sphere. So in the whole hard cell, how many atoms are there? One, right? Note it down. Now we have a sphere, and how many complete spheres are there? One, because there is one atom in this cube, simple cube, right? So what is the volume of the sphere? What is the formula for the volume of the sphere? Anyone knows? How to find the volume of a sphere? 4 by 3 pi r cube, right? Very good. So we have 4 by 3 pi r cube, right? So this is the volume of single sphere, and in the simple cubic unit cell, how many spheres are there? Only one. So multiply by 1, right? So this will give us what? The volume of the atoms within the cubic cell divided by the total volume of the cubic cell. So if this is A, one side is A and the structure is cubic, so it will be A cube, right? And you can see the whole thing here, it is written here. Now, here, this is R cube, right? And we already find out that R is equal to what? 0.5A. With you told me, right? R is equal to 0.5A. So instead of R, we have put this 0.5A and we take the cube of 0.5A. Now, once you simplify this one, what will happen? If you simplify this one, so it will be what? 4 by 3, 5, 0.5 cube if you write, and A cube divided by A cube. So A cube will be cancelled with A cube, and this one, if you do the calculation, what value you are getting? Multiplied by 1 because we have one atom. So what is the value you are getting? Do the calculation. 0.52, very good. So we are getting 0.52. Now what does it mean? It means that 0.52 is the atomic packing factor of the simple cubic structure. So what does this 0.52 represent? It represents that 52% of the space in the simple cubic cell is occupied by the atoms. The remaining 48% is free space, right? So it means almost half of the unit cell is free space, while the remaining half is covered by the atom. So this is what the atomic packing factor tells us, right? And this is how we find the atomic packing factor for the simple cubic structure. Is it easy? Clear? Okay, good. Now we are coming to the second one, the body center cube, right? The BCC. So the body center cube, as I told you, we have the same simple cubic, but inside the cube we have one complete atom. Inside the cube, when we have one complete atom, right? And that is known as the body center cube. Now the body center cube, this type of shape, the chromium, iron, tungsten, as well as several other metal exhibit this BCC structure. And here we have the 3D structure. If we take a simple unit of this and simplify it, it will be like this. Here, look, what we have the corner atoms, and inside the corner atoms, we have one complete atom. So we will know, we will now find how many total atoms are there, right? And the relation of A with R is this much. This one, A is equal to 4R divided by under root 3. We will find out it in the atomic packing factor. So the number of atoms in the unit cell of BCC. Now, can you tell me how many atoms are there? 2 atoms are there. Very good. So how 2 atoms are there? Same way, we have 1 over 8 of all these. So 1 over 8 multiplied by 8 plus this big atom, which is a complete atom, right? So plus 1, which is equal to 2. So in the body center cube, we have 2 atoms, right? 2 complete sphere we have. This is the number of atoms. The coordination number, a single atom is connected to how many other atoms? Yes, guys. Look here. 7. Look here to this sphere, the center one, right? Now the center one is connected to how many other atoms? 1, 2, 3, 4, 5, 6, 7, and on the back side is 1, 8. So it means one atom is connected to 8 other atoms, right? And same as the case, if you take this one will also be connected to 8 other atoms. How? Here it is connected to only 1, right? But this one, in the whole 3D structure, this one will be the center atom for other atoms, right? You have to imagine this. If you complete this in 3D, so this one, every atom is the center atom for some other atoms, right? So that's how every atom is connected to 8 other atoms, right? And you can see it clearly here. This is the central atom, and it is connected to 8 other atoms. This is the coordination number, right? Now the atomic packing factor, we have to find out how the atoms are closely packed there. So we will use the same formula, right? The formula is what? The volume of the atoms within the unit cell divided by the total volume of the unit cell. So within the unit cell, first thing, how many atoms we have? 2. Each atom is represented by a sphere, right? So sphere volume is 4 by 3 pi r cube. But the question is how this r is equal to 3a divided by 4. This is the important thing we have to understand, right? Now look here. If this side is a, right? So can we say that this one is half a? No, we cannot say. Why? Because here we have the free space, right? So we don't know this free space because now the atoms are not touching each other. In the previous case, look here to the sample cubic. Here they are touching, right? So A is equal to 2R. But in the body center cube, they are not touching each other. So we have to find the relation between A and R. How we can do that? Now look here. If we take this line from here to here, the diagonal line, right? In the cross way, like look here, from here I am going to this point, right? Not this point, diagonally I am going. So it is equal to how many radius are there in this line? Because this is touching this one and this big ball is also touching this one. So they are closely packed, right? So how many radius are there? 4 radius, right? 4R. Very good. Now, looking to the geometry, we have to find this 4R is equal to how many A? Now look here, if we make this triangle from here to here and then we go to here, but then we again come inside the things, right? Not on this side. Like look here, it will be much clear to you from here. We go here, we go back, and in between these two we go. So this is what this is, a triangle. Now in this triangle, we know that this side is equal to A, this side is equal to 4R, and this side we don't know, right? If this side we don't know, what we can do? This is the hypotenuse for this triangle. If we make this triangle, look here, from here to here and here to here. Look here, from here to here and here to here. Imagine this in 3D, right? So this is another triangle, this one. This is triangle number 2. And this is triangle number 1. Now in this triangle number 2, this side is equal to what? A. This side is also equal to A. And if we have two sides of the triangle, we can find the third one, this one, right? And we will find this one, and then it will tell us what is the 4R, right? So here I have done this calculation here. So this side, which is the hypotenuse for this one and this one, this is equal to under root 2A, right? If you do the calculation by Pythagoras theorem, so this is A, so this is equal to under root 2A, right? And this side, we know that this side is A. So now take this orange triangle. Now in the orange triangle, you have one side is this one, another side is this one, and the hypotenuse is equal to under root 3A. You know it, how it is equal, right? The hypotenuse, let's say the hypotenuse is X. So X is equal to under root, so X square is equal to under root 2A square plus A square, right? So square can be cancelled with the under root, and on A it will be there, right? So 2A square plus A square. So 3A square. And here it is equal to X square, which is our this side. So if again we take under root on all these, so this square can be cancelled with the under root, on 3 it will remain, and X will finish with the square root. So X will be equal to under root 3A. So A under root is only on the 3. And X is which side? This side. And we know that X is equal to what? 4R, right? So from this, what we have concluded? We have concluded that 4R is equal to under root 3A. 4R is equal to under root 3A. But here in the formula, we will not be putting 4R. We are putting R, right? Because the formula is what? 4 by 3 pi R cube. This is capital R, right? So R is equal to what? From this one, R is equal to under root 3A divided by 4. So under root 3A divided by 4, we put it here. And take the cube, but when you simplify it, the A cube will cancel with the A cube, and the remaining you put in the calculator, you will get a value. And do this calculation, and what values you are getting? .68. So 0.68 is what? 0.68 is the atomic packing factor of the BCC. Now, what does it mean? It means that within the BCC, right? This is the BCC, 68% of the space is covered by the atom, while the remaining, how much? 32% is free space, right? Like this one. So this one is more packed as compared to the previous one, right? The previous one was 52. So this is like the good packing of the atoms, right? In the BCC. So far better than the simple cube. Now, any confusion in the atomic packing factor of the BCC? Okay, very good. Now we have the face center cube, the FCC, right? So the crystal structure found for many metals has a unit cell of cubic geometry with atoms located at each of the corner and center of the all cubic faces. So we have the atoms in the corner, and on each face we have also atoms. So some of the familiar metals having this crystal structure are copper, aluminum, silver, and gold. All of them have what types of structure? The FCC. And in that hard sphere, the relation between A and R is this one, and this we will prove in the atomic packing factor, how it is equal to this, right? So here you can see the 3D, the hard sphere unit cell is this one, the reduced one is this one, and aggregate of many atoms, like the combination, all the atoms are arranged in this order. So this is what? This is FCC. Now here, the question is, how many atoms are there in the FCC? 7 atoms. Okay, how 7? Six and 1. Okay, so how 6? This is half atom, half, right? 1 over 2. This is 1 over 2. This is 1 over 2. And again, on every face, we have 1 over 2. So how many faces are there? 6. So 6 multiplied by 1 over 2. Plus, we have how many corners? 8 corners, right? So 1 over 8 multiplied by 8. So how much is it? It is 4, right? So total we have 4 atoms in the FCC, right? Total atom, if you combine all these and you collect it, it will become 4 hard sphere, 4 sphere or 4 balls you have in this hard sphere, right? So the number of atoms is 4. Now the coordination number. Here the coordination number, it is a little bit difficult to imagine, but you have to do this imagination with me, right? Look here, we are saying each atom is connected to how many other atoms, right? Each atom is connected to how many other atoms. So if we take example of this atom, so it is connected to how many? 1, 2, 3, 4 here, and then it is connected to the sphere 4, and come at in 3D. So in the another plane, it will be connected to 4 other atoms. So total, it is connected with 12 atoms, right? It is a little bit difficult to imagine, but do. Here I have found this photo. Here it is much clear. Now, if we take example of this atom, so look, it is connected to 4 atoms in the bottom plane, 1, 2, 3, 4, right? Then it is connected to 4 other atoms in this plane, 1, 2, 3, 4. And then it is connected to 4 other atoms at the top plane. So total number of atoms in the neighbors of one atom are 12. So the coordination number for this one is 12, right? So for better visualization, you can search videos on the YouTube. People have put a lot of videos. You will understand, right? And maybe you find some better image than this one. I tried, but I found this one, which I think it is much more clear, right? But if you cannot imagine, just search it, right? But the coordination number here is 12. So one atom is connected to 12 nearby atoms. Clear? Because this one, a little bit confusion, but I think you will understand. Now here we have the atomic packing factor. Same way we have to find the atomic packing factor. How we find? Look. The atomic packing factor, the same formula we have to use. What is the formula? 4 by 3 pi r cube multiplied by the number of atoms. How many atoms are there? 4. Divided by the volume of the sphere, which is a cube. But the question is, again, we have to find the relation between A and R. We have to find the relation between A and R. Now look here. In this case, it is not like the BCC. It is easy, even than the BCC. How? Look here, if you look into this side, we are not going to the back side, right? The corner, the front face. So all these atoms, these 3 atoms, 1, 2, 3, they are connected with each other, right? So we can say that this is we can add their radius, right? So 4r, we can say this side is equal to 4r, and we know that this side is equal to a because this is one side of the cube and this is another a, right? So 4r is equal to under root 2a by Pythagoras theorem, right? So it is easy. Now, so r is equal to what? R will be equal to under root 2 divided by 4a. So this is r. Now this r, we will put it in the formula. And here you see under root 2a divided by 4 whole cube. And when you simplify it, a cube will be cancelled with the a cube, and the remaining, if you put it in the calculator, you will get the value. What is the value? .74, right? And 0.74 is the atomic packing factor for FCC, which means 74% of the space in this cube is occupied by the atoms, while the remaining 26% is free space, right? So that means this one is more even dense.